So in this video, I'll look at the essential skills required to carry out basic regression analysis of some time series data. So I'm going to read in a time series data set here in the usual way from a CSV file. Now, if you have a look at that in the environment, here's where you can see your objects. You can see that's come into a data frame. If we click this little icon here, we can look at the data. So it's got three variables, Q for quantity, K for capital, stock, L for labor force. So I'm estimating a simple production type function. Now notice it has a variable called year, but actually I want it's best in R. In fact, I think you have to do this. You need to create your own time variable to use rather than this one. So to do that, and let me just go back to the source editor. So you use this TS function, and for this you specify the data frame, the start date, which if you remember was 1960, and the frequency, in this case 1 for annual. Obviously if it's quarterly you put 4, and in that case for your start date you put a little vector with the year and the beginning quarter. So for example 1960, 3 in a little vector. But here it's annual. I don't need that. Just put the start year. Now notice this here as well. This is what I'm doing here is I'm using the data frame, but not including that first column, because of course that has got the years in it, which I don't want. I'm going to create my own time variable, which you need to do using the TS function. So what you do is you put FDT brackets, comma, which stands for all rows, -1. So that's telling me to use all the rows, but ignoring the first column, which is what I want. So if I run that and store this in a variable FDT, and then if we have a look at that, as you can see, we've now got a time series rather than just a data frame with telling me the start and end date, the frequency. Here's my variables, and here's that time variable, that implicit time variable that I've created, which enables R to recognize this as time series data and draw graphs appropriately. So a quick summary here, just to get some descriptive statistics if you want them. If you want to have a look at the data, a simple way, simply use plot.ts, which stands for plot time series, on your variable containing your time series, which notice is FDT as well. Notice I stored this new time series in the same variable, so I replaced what was in there. You could have used a different one. And there we get them. They plotted on top of each other. Notice how it's picked up that time variable. It even puts the correct label because it knows it's time. And those are the three variables. You could, of course, change the main heading here with the main function, main option, as we've seen before. Just note, in fact, that if you look at the FDT now, it's now doesn't say data frame, it says MTS, matrix time series. So it's actually a different type of object in R. It's a matrix time series, which therefore has to be treated as such. So this is why you'll need to use a matrix type notation if you want to subset it and so on. Now to plot a scatter graph, we've seen this in the previous video. It's plot and then the variable on the vertical axis, tilde on the horizontal. You could just leave it at that. Of course, sorry, you need to specify the data, where the data is in FDT. You could leave it at that, but if you want a specific title, use the main function. This PCH option changes the style of the plotted points. Different numbers give you different things. And the Y lim I've seen before sets the Y-axis scale. Obviously, if you want to set the X-axis scale,
you'd use xlim, but you don't need to do that here because it'll pick it up from the time variable. So that gives me a nice scatter graph with a proper title and a better scale, because it didn't need to go down to 0, and I've changed the default dots to a cross with this option here. Now, a lot of the time with time series data, you want to estimate a relationship in the natural log of the data rather than the actual levels themselves. So you can easily do that using the log function. So here I'm using the log function on my data set to create a new data set of logs like that, which I'm calling lnfdt for natural log. If you have a look at that, you'll see we've now got a time series, a matrix time series with logs in. Now, in order to run regressions involving differences and lags, which typically you often want to do with time series data, you cannot use the base RR function LM, which I used with cross-section data. It doesn't handle lags and differences. You need to use a different one. And there are various packages you can use that will enable you to do this. The one I like is simply called din. So I'm going to load that into memory. Obviously, you'd need to make sure it's installed. I'm now going to create a time trend variable, which I want to use in one of the regressions. Again, I can do that using the TS function. So simply state TS and then give the range of values that you want. I want this time trend to run from 1 through to 20, 1 to 20. And since it's a time series, I need to specify the start date. Don't need the frequency here because it knows it's going to be annual. So I'm going to create, that's how you can create a time trend variable. As you can see, it has to be a time series because I'm going to include it as part of my data set. And that's how we do it. Now, if I want to add this time trend variable to my data set, since this is a matrix, FDT is a matrix, not a data frame, I can't use the list notation of a $sign. I have to use cbind, which stands for column bind an extra column into it. So you put cbind, the data set, comma, and then the new variable or variables. And then I'm storing that again in lnfdt, so I'm replacing what's in there. And if we have a look at that, as you can see, it's now added that time trend variable into my matrix time series. But notice that it rather messes up the variable names here. So you can easily change that by using the call names function. So you simply put call names and then in brackets the data set, and then assign to that a vector containing the new variable names that you want. Of course, put these in the same order as the actual columns in your data set. So I think you can see here how to change the column names, use the column names function. So if I do that and then have a look at it again, as you can see, now we've got these nice neater variable names. I'm using a lowercase letter here to remind me that these are logs, rather than I used a capital letter here for the original variables. So using a small letter is a good way to remember that it's now in logs. Okay, so now that's how to set up your data set, how to turn it into a matrix time series, add a time trend if you want, how to put it into logs, and so on. So we're now ready to do some analysis. So I'm going to run a regression here of the first difference of Q as my dependent variable, and my independent variables, my regressors will be the, I'm going to run a regression first of all using the first difference of labor variable as my dependent variable, and my independent variables will be the time trend variable and the first lag of L. This in fact is a type of what's called an augmented Dickey Fuller test relationship. If you know what that is, you'll recognize this. But it doesn't matter. All I'm doing is illustrating here how you can use the diff function to get the first difference, and the lag function here to get the first lag. So notice diff on its own always gives you the first difference. If you want a second difference, you need to specify an additional option. But lag, on the other hand, if you need to put lag and then the name of the variable you want to lag, L, comma, and then a -1 to get the first lag, obviously -2 to get a second lag, and so on. So it's the same effective syntax as the LM, except you put dyn $ in front. This won't work, of course, unless you've loaded up the dyn package. So provided you've loaded that up, to enable to run a regression involving differences and lags, you can't just use LM, it won't work. You need to use this din package and use dyn $LM, and then it's pretty much the same as before. You specify your dependent variable, in this case first difference of L, tilde, and then your independent variables separated by commas. So the time trend, by plus signs, the time trend and the first lag, and then of course you specify the variable containing your data set. So running that and storing the results in fmod1, we can then have a look at a summary of it. And as you can see, we get the standard printout, and it's correct. It's worked correctly. I say if you just try to do it with LM, it wouldn't work. It doesn't like differences and lags. So you need this dyn $LM, and to do that, you need this package dyn. Okay, so that's how we can run a regression. Now, if we want to do some diagnostic testing, then first of all, let's plot the residuals. Well, we saw in the previous video how you can use the residuals function on your summary, on your results, to retrieve the residuals. So I've got residuals, brackets fmod1, and then I use the plot function on that. So notice that it's plot, and then in brackets residuals, brackets fmod1. So that's going to plot the residuals like that. Now, a nicer way, in fact, to plot the residuals and also to get an autocorrelation function diagram, a correlogram, and a histogram of the residuals, is to use the check residuals function, which is in the forecast package. This forecast package is a very useful package for doing forecasting from time series data, as the name suggests, but it does have lots of useful other features, if you're interested in doing any forecasting with time series data, I recommend this package. So I'm going to load that into memory, which then means I can use the check residuals function in there on my results, fmod1. And as you'll see, what we get is a nice little printout here with a plot of the residuals, and it's in a much nicer style than I had up here, because it's using what's called ggplot2 to get this style. If you want to know more about how to use ggplot2, look at my videos. You also then get the correlogram, the autocorrelation function here, and also a histogram of the residuals. So you get a nice set of useful diagrams here for assessing whether residuals are random or whether they're correlated, whether they're normally distributed. It also, if you go back here to the console by default, does a Broch-Godfrey test of zero correlation, but it chooses the order itself, and this won't normally be the order that you probably want to test. I wouldn't want to test with this annual data here, sixth order autocorrelation, which is what it's chosen here. I'll show you how you can do your own tests in a moment. But as you can see, that does give you a nice printout. So we can see here from the article here, there doesn't appear to be any correlation. in any autocorrelation here in the residuals. These look fairly random as well. Now we can test that formally. Of course, one thing we could do is to run a box test, a Ljung box test, I think it's called, on the residuals, which of course is a joint test of significance. So you do that with the box.test function. So you run that on the residuals. So again, retrieve the residuals. You might want to actually run this function here and store the results in a variable so that you can just put the variable name in rather than having to put residuals brackets f mod 1 all the time. But you can do it this way. Then you specify the lag, in other words, how many autocorrelations you want to jointly test, and then you say the type is Ljung, I think that's how it's pronounced, Ljun. So that's going to give me a box Ljung test there of up to fourth order. So it's jointly testing the 4. They're jointly equal to 0, and that's not rejected. So again, that's indicating no autocorrelation here. Finally, of course, we could run a Breusch-Godfrey test. Say this one it does by default in the check residuals function. It's not really generally useful because I don't want to test up to 6th order. What I want to test here, being annual data, is 1st order and 2nd order. So for that, we need the BG test function, which is in this package lm test. I mentioned this package in the previous video. It's an essential package for doing regression analysis because it contains all the standard diagnostic and specification tests. So make sure you have this package. Let's load it in. Then we can use BG test to run a Breusch-Godfrey test on our results here. Notice you don't specify the residuals, you just specify the results variable. It picks up the residuals automatically. By default, that gives me first order test. If I want second order, third order, and so on, simply use this order option here. So for a second order, put order equals 2. And you can see that's second order. And notice both of these are not significant. So there's no indication of autocorrelation here. Okay, very quickly, let's look at how to run a slightly more complicated regression. So here, again, I'm using dyn$lm, but this time notice that I'm subsetting the data. So I'm rather than using the full data set, but of course remember that when you use differences and lags, that does reduce the number of observations. So here I'm specifically wanting to only use the data set from 1962 onwards rather than 1960. So you do that by using this window function here. And in fact, the window function is how you can actually subset your data if you want to actually create a subset and store it in a variable. But here you can put it directly into the dyn$lm function. So my independent variable this time is first difference of q, but notice around that I'm putting this windows function to make sure that it only uses data from 1962 onwards. So you put window and then in brackets and this is inside this din$lm function, of course, window, brackets, and then the name of the dependent variable, comma, and then the start value. And then from then on it's the same as normal, tilde, and then the independent variables separated by plus signs. So I've got the first lag of q, the first difference of k, the first lag of q, the first difference of l, the first lag of l, and then of course specifying the data set. So this in fact is a first order error correction model. Again, if you know what that is, you'll recognize it. If not, it doesn't matter. You can see how you can specify a fairly complicated model with a number of lags, a number of differences, and so on. And notice how you can subset use a smaller sample, a subset of your sample here using this windows function. So running that, storing the results,
having a look at them. As you can see, that's worked fine. And now, of course, we can run the same test, the Broish-Godfrey, order 1, order 2. Now, it's less typical, of course, with time series data to run into the problem heteroscedasticity. That's usually more with cross-section data. But if you want to test for that, of course, you can, as we saw in the previous video, you can use the BP test function in LM test package like that. And finally, you might want to run the old Durbin-Watson statistic, because that is not printed out by default. Notice in the standard printout, with some packages it is. Some software like eViews and so on, I think it's by default. But it's not by default. So if you want to run it, just use DW test function from LM test package, and you get the DW test. So as you can see, it's possible to run some very standard regression type analysis on time series data in R.